Well, next we'll be discussing about the 16th question, and that's about projectile motion. Consider an object projected at an initial velocity of u while creating an angle theta with the horizontal. The horizontal range of the projectile is r. Which of the following graphs correctly represents the variation of r with u? All right, so when you project an object like this at an initial speed of u, we know it's going to take a projectile path like this, and then eventually it's going to end up here. The object is going to end up here, right? And this angle is theta. Now, if we ignore air resistance, which we normally do, the projectile path will be a very symmetrical one, and this is what we call the horizontal range. Fine. So the equation for that is r. I mean, the symbol we use that is r. Time here it's 0, and when it reaches the time of flight, let's say it's t. And for r, there is an equation that is 2 u squared sine theta cos theta divided by g. Now, for such MCQ questions, if you can remember this equation, it will be very convenient, directly, very straightforward. The answer is very straightforward. But if in case if you are not aware of that equation, I'll take 1 minute and quickly explain it. Now, first of all, you have to take the components of the velocity, initial velocity, that is u sine theta, the vertical one, the horizontal one is u cos theta. Right. Now, to find out r, we need time. For that, what I'm going to do is I'm going to apply s equals ut plus half at squared for the entire motion. I'll say this point is A and this point is B. So we are applying the equation from A to B, and that is vertically upwards. If you see from A to B, the vertically upward displacement is 0 because the object hasn't gone above this level. We have to compare only the starting and the finishing point. This is the starting point, finishing point. It hasn't gone neither up nor down. Therefore, vertical displacement is 0. Initial vertical velocity is u sine theta. Total time taken is t plus half into, we know there's only one acceleration which is going to influence this motion, that is gravitational acceleration, because we are ignoring air resistance. Right. So you take this to the other side, it's going to be gt squared by 2 equals u sine theta t. One of the t's can be cancelled out, and you will end up in t equals 2u sine theta divided by g. That is the equation for time. And then you apply the same equation horizontally. S equals ut plus half at squared. Right. Horizontal displacement of the object from A to B is capital R. That is the range, horizontal range. And the horizontal initial velocity component is u cos theta into time is this 2u sine theta divided by g, plus there is no horizontal acceleration if you ignore air resistance, so we can take it as 0. Therefore, r is equal to 2u squared cos theta sine theta divided by g. That's the equation I had already written. So if you can remember this, it's easier when you handle MCQs. But if you are unaware of that equation, maybe here's the explanation for that. And now you can see the important part now. The relationship between r and u is given by this. That is, r is proportional to u squared. I mean, why do I say that? Because an initial speed u, and while creating an angle theta with the horizontal, they are saying creating an angle theta with the horizontal. So we can consider that theta, g, they are constant values because they are not changing them. We have to plot the graph for r with u. So if theta and g are constant, if theta is constant, sine theta and cos theta should be constant. 2 is a number, it's constant, g is also constant. Therefore, we will end up in a relationship like this: r proportional to u squared. R proportional to u squared. All right. So another quick revision: if you have a relationship like this, y is proportional to x, and for that relationship, if you plot y and x graph, it will be a straight line going through the center. That's the first thing. And if you have a relationship y proportional to x squared, for this relationship, if you plot the graph for y and x, okay, y depends on x squared, so the graph will bend towards y like this. And at the meantime, if you have a relationship like this, y is proportional to root of x, or you can say y squared is proportional to x. For such a relationship, the graph you plot for y and x will look like this. And sometimes we come across a relationship like this: y is inversely proportional to x. For that, the graph will look like this. So these are very common graphs you will come across in physics in future lessons. You have to have this idea in your mind. Okay. So here you can see R is proportional to X. That means we are talking about this shape, isn't it? We are talking about this shape. Therefore, answer for this question should be 4. If you remember this equation, it will be very straightforward. Well, the next question is the 17th one. Let's go through and see what this question is all about. A circular shaped tabletop of 50 kilogram mass and 4-meter diameter is placed on two legs, which are 1 meter in height and separated by a distance of 3 meters. So you can see it, everything is given in the diagram, 4 meters. Now they are looking at this from the side, okay? Even though this is a circular tabletop, if you see it from the side, it will look like this. A person is seated at A. So a person is seated at A, right? So this is the person seated at A. Find the maximum mass the man can have so that the table does not topple. The answer should be in kilograms. So these are kilograms. Consider that the force exerted by the man on the table acting along the edge of the table vertically downwards. Okay. Now a man is seated here. That is the maximum possible man with the maximum possible mass without toppling the table. So the man will be seated here. There will be force. That is his weight actually. mg. We have to find m. And this is a tabletop with 50 kilogram mass. Therefore, I have to mark the weight of the tabletop exactly in the middle of this. That will be how much? 500 Newton. 500 Newton, which will be at a distance of 1.5 meters from this point. 1.5 meters from this. I'm assuming it's a uniform tabletop, so 1.5 meters. If it's a uniform tabletop, the weight will be exactly at the center. 4 meters is total length from the center of gravity to the cone. It's 2 meters. Therefore, this small distance has to be 0.5 meters. This small distance has to be 0.5 meters. All right. Now we all have to understand one thing. What is it? Tabletop at the verge of toppling. Now we have to consider that situation. Tabletop at the verge of toppling. If the tabletop is at the verge of toppling, what's going to happen now? If tabletop is going to topple, if the man is seated here, this part is going to go down, this part is going to go up. Here it's going to go up, here it's going to go down. Right? That's common sense. Right. So when the tabletop is at the verge of toppling, why am I using the term at the verge of toppling? Because they are asking for the maximum mass of the man. Therefore, we can assume that this part's connection is the contact actually. The contact of the tabletop with the leg at this part is almost vanishing. It's almost disappearing. Therefore, you can say R is 0 at this point. R is the perpendicular reaction. There will be a perpendicular reaction between two surfaces if there is contact between those two surfaces. So in this case, we have to assume that R is 0 there. Okay, so you have everything lined up for you, and I'm going to take moment about this point so that I don't have to consider the perpendicular reaction acting here. I take that point as X, and there aren't any other forces acting here. That's all. There is a force. There must be a force marked here, but in this particular special situation, that is 0. So all you need to do is for this condition, for this situation, take moments. So clockwise moment about X. That should be equal to counterclockwise moment about X. All right, so what is clockwise moment over X? That will be mg multiplied by 0.5 meters equal to counterclockwise moment about X is going to be 500 into 1.5. Fine. So g is actually 10. Then you can cancel out that g with one of the zeros here. And 0.5 and 1.5, you can make them 1 here and 3 here. 50 into 3, and the final answer is going to be 150 kilograms. And you can settle to the fourth answer. Fourth one will be the correct answer for this question. Moving on to the 18th question. Blocks P and Q have masses of m and 2m respectively. They are connected to a light string balance, a light spring balance, a light spring balance. That's very important. So the spring balance doesn't have mass and kept on a smooth horizontal plane. Horizontal forces F1 and F2, where F1 is larger than F2, are applied to P and Q respectively. So they are applying F1 to P, F2 to Q. F1 is bigger than F2. There is no friction. Therefore, the system is going to move towards left, and that's what they have indicated here. So I'll put another arrow and make it the acceleration of the system. If not, let's forget about that. Each object is going to accelerate this way. All right. If the system moves towards left with constant acceleration, they have mentioned that if the system moves towards left with constant acceleration, the reading shown in the spring balance will be the reading shown in the spring balance. So they have mentioned the fact that the system is moving to the left at constant velocity. So the entire thing is moving to the left. Right. So the spring balance reading. Now this is a light spring balance. Therefore, we know now when P tries to go to the left, what will happen? The string will pull it to the other side. So these are the forces acting on P. And now, if Q is going to the left, definitely there must be a tension acting on it to the left. Then only it can move to the left, for that matter. All right. And when it comes to spring balance, this tension is going to be the reading, and the tension at this point. I mean, when you have a spring balance, you normally connect the object on this side, correct? Like this. So whatever the tension we have here, it's going to be the reading, not the other side. But luckily this time, since the spring balance is light, either side the tension will be same. If the spring balance had a weight, then the tensions would have been different. You should have taken it as T1, T2. For that, then they should have given the mass of everything. Still, we can find this tension here separately. But since they are mentioning the fact that it's a light spring balance, we can, without any doubt, we can mark the tensions on either side of the spring balance equal, and just finding that tension is our task. All right. These kind of questions are pretty straightforward. What do you do first of all? Horizontally, the system is moving to the left. So to the system in that direction, for the entire system in that direction, I will apply F equals ma. Right. What is the resultant force acting on the system in that direction? That should be F1 minus F2. There's no point of marking tension because tensions, these two will cancel out. And the mass, total mass, I think it's m plus 2m. Careful, m plus 2m. P is m. And Q is 2m, right? M plus 2m, that is okay. Into acceleration, the total acceleration of the system, A, right? So I can say F1 minus F2 divided by 3m, that is equal to the acceleration. Done. And then you can choose one of the masses. Now, choosing any mass is fine because both the masses are experiencing two different forces horizontally. Therefore, any mass would be fine. So let's apply for P first. For P, I'll apply F is equal to ma again towards left. So what are the forces acting on P horizontally? F1 minus T. Be mindful about the direction. F1 minus T equals mass of P is m into, for acceleration, you can substitute this. That is going to be F1 minus F2 divided by 3m. F minus F2 divided by 3m. So this m and m can be cancelled out. And now it's time for us to find the expression for T, tension, right? What do we do? F1 minus T, that is equal to, I'll divide each one by 3, so it will be easier for me when I simplify F2 by 3. Then I'll take T to the other side, the other things to the other side. F1 minus F1 by 3 plus F2 by 3 equals to T. So finally, we will be getting T is equal to F1 minus F1 by 3 is 2F1 by 3 plus F2 by 3. That is, they have taken 3 as the common denominator. Therefore, we will be getting this. Easy. If you want to try it with Q, we still should be getting the same answer. Let's see. Q is also moving to the left, right? But what are the forces acting on Q now? To the left, T minus F2, and that is equal to ma. Then for m, you had to carefully put 2m. That is the mass of Q multiplied by F1 minus F2 divided by 3m, right? So it's T minus F2 equal m and m will get cancelled off. If I multiply everything, 2F1 by 3 minus 2F2 by 3. And then T stays here, F2 goes to the other side. 2f1 by 3 plus f2 minus 2f2 by 3. And you will end up in the same equation, won't you? 2f2 by 3 plus f2 by 3, because f2 minus 2f2 by 3. Therefore, if you take it as a common denominator, again, you will end up in the same answer. That is 2f1 plus f2 divided by 3. Hence, careful. The answers are looking alike, so you have to carefully choose. The answer is third. Answer is third one. Okay. And the next question. It's again a question under the projectile lesson. An artillery gun kept on a horizontal flat surface fires shots at a constant speed. That's important, constant speed, while creating different angles with the horizontal. So you can change the angle with the horizontal, but the speed cannot be changed. If the maximum horizontal range, it should be range as printing error here, maximum horizontal range of the projectile is L, find the horizontal range when the angle created with the horizontal is 30. Now, this is interesting. Since I explained you earlier the equation for horizontal range, hope you all can remember when the initial speed is u and then the angle is theta, and when you fire the object, it takes off a projectile path like this, and the range, the horizontal range is given by the equation r equals 2u squared by g sine theta cos theta. We in fact derive this, so I'm not going to do that again. Remembering this, it will be helpful for you when you do MCQs. That's why I said. Anyways, let's move on. Now, this is a key point. Maximum horizontal range of the projectile is L. Maximum for maximum range, what's the condition? For maximum range for a given speed, why am I saying for a given speed? Because they're saying the speed is constant, right? Theta must be 45 degrees. This is a fact you have to remember. Very, very important in a projectile motion. If you want the maximum horizontal distance, then the angle must be 45 degrees, right? Fine. So if you want to hit a 6 and if you want the ball to land as far as possible, that means you have to find a way to hit it at 45 degrees. But the problem is, in reality, I don't think that calculation would be the best. But still, yeah, it works. It would work because we can't apply this equation in reality, because in reality we have to account for air resistance and stuff. But still, my point is, if you want highest range, you need the angle to be 45 with the horizontal. Now, they have given us a symbol for the maximum range, that is L. So I'll start with this equation itself. R equals 2u squared over g sine theta cos theta. All right. So R maximum, that is equal to L, and that will be 2u squared divided by g, and u squared by g into sine 45 into cos 45. Why am I putting 45? Because that's when the range is maximum. Then theta is 45. Okay, then if you substitute the values, you will see 2u squared by g into 1 over root 2 into 1 over root 2. Those are the sine and cos values of 45 degrees. And root 2 into root 2 is a half into 2 is 1. Therefore, you will be getting u squared by g. That is the equation for the maximum range, u squared by g. And from this, what is the conclusion? L is equal to u squared by g. Okay, right. Now we are supposed to find out the equation, if the range when the angle is 30 in terms of L. Now I'll use the same equation when theta is equal to 30. All right, what will happen to the range now? Range will be equal to 2u squared by g multiplied by sine 30 into cos 30. Right. So that's going to be 2u squared by g multiplied by sine 30 is half, cos 30 is root 3 by 2. Correct? Root 3 by 2. Then if you simplify that, r is equal to, I'm taking r, not r max, r, this is the angle, r at 30 degrees angle. This 2 and 2 can be cancelled out. Therefore, it's going to be root 3 u squared over 2g. That is the equation I'm getting for range, horizontal range, when the angle is 30. Good. And instead of u squared by g, you can use the term L. You can use the term L. Therefore, R is going to be equal to root 3 by 2 L. Because instead of u squared by g, you can substitute L. Why am I doing that? Because look at the answer. Answer is in terms of L. Therefore, we can go with the first answer, can't we? And go with the first answer. So this is a fact you have to remember. I'm not going to prove it here because it's going to consume time unnecessarily. Just go through your theory parts. You must have come across this. Okay, another projectile question. That's the 20th one, following the 19th one. As shown in the figure, an object of mass 0.1 kilogram was projected at a speed of 10 meters per second. Right, so u is 10. What is the change in momentum of the object when it leaves the ground at point P and reaches the ground at point Q? Ignore air resistance. When you ignore air resistance, you should know that when the object reaches the ground, it will have the same speed while creating the same angle with the horizontal. That's something you have to know because the path will be symmetrical. Path will be symmetrical if you don't consider air resistance. Therefore, this is the final velocity. Okay, right. They're talking about momentum. It's a vector, remember. Now there we have to find out change in momentum. Let's start then. Change in momentum. Now what's going to be the equation for change in momentum? That is going to be final momentum. Where is the final momentum? I'll say within bracket at Q minus initial momentum. Momentum at P. Right. Now, what is the final momentum at Q? Momentum is a vector. So, shall we substitute the values here? Now, at P, if you consider at P, take momentum. What's going to be the momentum now, guys? That's going to be the velocity is 10. Its mass into velocity, that is 0.1 into 10. And that's equal to 1 kilogram meter second minus 1. But remember, the direction is very important. Like this, 45. So at this point, we don't have to waste time. Momentum, it's going to be still 1, but the direction is going to be different. No? So 1 kilogram meter second minus 1, but in this direction, 45. All right. So the final momentum is in this direction, 1 kilogram meter second minus 1, while creating 45 degrees to the horizontal. Right, minus what is the initial momentum that is in this direction? That is the magnitude of that is also 1 kilogram meter second minus 1, while creating 45 degrees to the horizontal. Right. So when you have two vectors creating an angle with the horizontal or vertical, always we go for the components, don't we? Now, what are the components here? The vertical component is going to be 1 sine 45. Which is actually 1 over root 2. And what about the horizontal component here? That is 1 cos 45. Again, 1 over root 2. Similarly, here, the vertical component is going to be 1 sine 45, and that is 1 over root 2. And the horizontal component here, that's going to be 1 cos 45. What is it? Again, 1 over root 2. So instead of 2 momenta, I have taken components of momenta so that we have 4 now instead of 2. You can forget about these 2 and consider only the components. Now, if you look at the components carefully, look at this one. 1 over root 2 to the right minus 1 over root 2 to the right. So these 2 will cancel out each other. Because you are subtracting, yeah, minus sign. So you can cancel out this and this. Because they are both in the same direction. So when you subtract, they will get cancelled out. 1 over root 2 minus 1 over root 2. That's it. But the vertical components, you have to be a little careful now. Vertical components. Why is that? Look at the vertical components. In this one, the vertical component is downwards 1 over root 2 minus, sorry, we are dealing with vectors, not just ordinary numbers. 1 over root 2 minus this minus sign here. Minus here it's upwards 1 over root 2. Yeah, now both are 1 over root 2, but the answer is not 0 because the direction is different vectors. If it was a scalar, 1 over root 2 minus 1 over root 2 is 0. But since it's a vector, you have to consider direction. Now, if the directions are different, it's better to change the direction to the same side. So it's one over downwards 1 over root 2. Minus upwards can be written as plus downwards 1 over root 2. All right. So what's going to be the final answer? We have to add root 2 plus root 2. 1 over root 2 plus 1 over root 2. That is 2 divided by root 2 downwards. What is 2 divided by root 2? That is in fact root 2 kilogram meter second minus 1 downwards. They're not asking you for the direction. Sometimes they might ask you for the direction as well. But since we need only the magnitude, we can safely choose fourth as the answer. But my personal opinion would be you should have a very good idea about the direction as well, right? Because sometimes in another question they might give you root 2 upwards, you root 2 downwards, both, and you have to be absolutely sure what the direction of momentum is, right? This is something you have to be careful. Take components, and when you subtract, make sure you consider direction. If not, there's a possibility of you getting it wrong. Now the next question we will be discussing is 21st question, and let's see what that question is all about. Two blocks of mass MA and MB are kept on a smooth horizontal table as shown in the diagram below. The maximum frictional force which can act between the two blocks is given by F. Okay. When a gradually increasing horizontal force was applied on MA, the blocks started slipping on each other when the value of applied force is F1. And when a gradually increasing horizontal force was applied on MB, you can see it's applied on the block at the bottom. The blocks start slipping on each other when the value of applied force applied force is F2. The correct relationship between F1 and F2. So we have to find out the relationship between F1 and F2. The important thing in this question is the table or the surface on which the blocks are kept. That surface is smooth, but between the blocks there is friction. Between the blocks there is friction. So you can't mark a frictional force at the bottom. You have to make sure you understand that. Okay, fine. Now, so if you analyze this is what's going to happen. When you apply a force here F1, when you apply a force here, a friction will act on MA in this direction. So I'll mark that in green color, the force acting on MA. All right. And the same force will be acting on MB in the opposite direction. I'll mark it in blue color. All right. So we are allocating blue for B, green for A. These are the forces which are going to be created. And here, what's going to happen now? When you apply force F2, what's going to happen, people? There'll be a friction now when you MB will be trying to move to the right, so there'll be a friction acting on this to the left, isn't it? Yeah. Now this way. And on MA, there will be another force acting this way. Same value, but in the opposite direction, frictional force. Newton's third law, action-reaction pair. All right, fine. Now talking about the forces, right? So I'll just mark that as FF, the frictional force. Frictional force. Now, both the objects will move together until this friction acting is, this friction acting is less than the limiting frictional force until that point. Okay, now if you see practically, if you push this object like this to the front, there's no other force acting in the system. If you consider the whole system, look at the resultant force, just F1. So the whole system is going to accelerate to the right with an acceleration of A. And here also same thing is going to happen. Okay, so now let's say the blocks are at the verge of slipping. When the blocks are at the verge of slipping, what's going to happen now? Yeah. And the blocks are at the verge of slipping. When you apply a force, both the systems are going to move because the bottom part is smooth, not because both the systems are going to move. When blocks are at the verge of slipping on each other. right? What's going to happen now? Slipping on each other. If you take the first diagram, your force acting on the object should be, the frictional force should be, FF should be the first diagram, A, figure A. That one FF should be equal to simple F. They have given a simple F. Similarly, in figure B also, okay, in figure B also, it's going to be similar, isn't it? Because that's when the object is at the verge of slipping. Okay, fine. So I think it would be better if we draw free body diagrams for better clarity. I'll quickly draw it. Now, we are considering when the blocks are at the verge of slipping on each other. So when the blocks are at the verge of slipping on each other, we all have to understand that the friction acting on between each block has to be the limiting frictional force. I think we all can agree with, you all can agree with me on that. So for figure A, if I draw it again, I'll draw it, I'll draw free body diagrams now. MA and then MB. Okay, people. Right now, force is applied on MA. This is MA. Okay, this is MA. This is MB. I'm explaining you figure A. Okay, 2 pair A. Figure A. Right. Now we are applying a force on MA. That is F1. I'll mark the force acting on A as A in green. Right. Fine. So there is a force F1, and because of this F1, MA will try to slip to the right. Therefore, there will be friction acting on that in the opposite direction, and that is simple F now, because the object is at the verge of moving. So same force will act on the other object, that is MB, in the forward direction. All right. So I think I should have taken the accelerations A1 and A2. We don't know whether they're equal or not. Right. A1 and A2. Okay. So both these objects, very important, will have the same acceleration towards right. They both will be moving at same acceleration towards right. So the acceleration of this is going to be A1. The acceleration of this is going to be A1 to the right side. All right, fine. This is the system. When this system is at the verge of slipping, when the blocks are at the verge of slipping on top of each other, when the blocks are at the verge of slipping on top of each other, the friction between them is the limiting frictional force, and it's mentioned there. The maximum frictional force which can act between the two blocks is given by F. Right. Now, if you take this diagram, figure B, if you draw a free body diagram for figure B, let's see what's going to happen. So this is MA, this is MB. Right. Now, talking about these two, you look closely. This is MA and this is MB. Now, we are applying the force to the bottom block, MB. Therefore, F2 should be marked here. F2 will be acting here. Because of that force, a friction will act on F2 in the opposite direction. Actually, it will be acting in this direction, correct? In this direction. Simple F. And an equal and opposite force will be acting on MA. Newton's third law. How did I mark these two forces? Based on Newton's third law. These two forces were marked based on Newton's third law, right? And MB and MA both will be accelerating towards right with acceleration A2. I hope now it is clear. I hope now it is clear. So friction must be marked wherever the, first of all, it should be marked wherever the force is applied. Based on that only, you have to mark the friction. So I think now the free body diagrams are clear to you. One more time very quickly. Force F1 is applied on MA. Therefore, MB will try to stop it from moving to the right. Therefore, a force will act in the opposite direction on MA. And according to Newton's third law, if this F is given by MB on MA will give the same force in the opposite direction on MB, Newton's third law. Here what's happening? We are applying the force to the bottom block. Therefore, MA will try to stop MB so that it will create a friction in the opposite direction. According to Newton's second law, MB also will create an equal and opposite force on MA. That is also F. So this is the system, right? Now let's consider these two systems separately, and we'll find out F1 and F2. That's going to be our task today. Finding the values of F1 and F2. Right, fine. Now for this entire system, for the system, I'll apply F equals MA. Okay, to this system. So what is F? To the entire system, just F1. Why is that? Because this F and this F will get cancelled off when you consider the entire system. For mass, we have to put MA plus MB, and then acceleration is A1. So I'll leave it like that. Guys, remember we have to find out F1. We have to find out relationship between F1 and F2. So I'm not going to get rid of, I'm not going to make A1 the subject here. I will leave A1 as it is. Now I have to find A1 and substitute a value here. To find A1, the easiest thing you can do is applying F equals to MA for MB. Why am I doing that? Because look at MB, only one force is acting on MB and that single force is F. So in the right side direction, simple F is equal to MB A1. So what is A1? A1 is equal to F divided by MB. F divided by MB. Then let's substitute it here. That will be F1 equal MA plus MB into F, simple F actually, simple F over MB. This is the equation for F1. So I have an equation ready. I need to get an equation for F2 just like this and compare those two values. That's it. Let's go back here. Right, I'll use another color for this. If you take this system, for this entire system, let's apply just like this. F is equal to MA, all right, towards right. What is your resultant force on the system? F2. Because if you take the whole system, simple F and simple F will cancel out each other. And for M, again, we have to put MA plus MB, that is the total mass. And for acceleration, I'm going to use the term A2 now. Right, I can't take the accelerations equal. You can't say that, surely. All right, I've taken it as A2. Now let's try to find out the value for A2. Okay, how do you do that? Now which object will you choose? Now you should be choosing MA. That's the easiest method, MA. If you choose this, it's not wrong, but my advice, choose, go for, don't make the calculations complicated, right? Now earlier I chose MB. Why is that? Because only one force was acting on MB. Here, only one force is acting on MA, therefore I'm choosing MA, applying F is equal to MA horizontally towards right. What is the only force acting on that? Simple F. And what is the mass of that? MA into A2. Therefore, A2 is actually simple F over MA. Right. Finally, you will get F2 equals MA plus MB into A2 is simple F over MA. Right. So these are the two equations we have acquired. Now, I'll just highlight them. This is F1 and this is F2. So by the looks of it, you should be able to understand MA plus MB into F, MA plus MB into F is common for both, right? It's common for both. And F1, we have MB as the denominator, F2, MA as the denominator. All right. Then what will be the comparison? Never mind, I will quickly write that again and do the comparison. Right. F1, the equation F1 is going to be, I'll just write, okay, F over MB into MA plus MB, F2 equals F over MA, brackets MA plus MB. We know now MA plus MB into F is common for both the equations. MA and MB, you can see MB is bigger than MA. Since MB is bigger than MA, what should be the conclusion? Now, when the denominator is large, what's going to happen to the fraction? When this value is large, this value will be small. When this value is small, this value is going to be large. So the final verdict is going to be F1, it's going to be smaller than F2. F1 is going to be smaller than F2. So we can settle to this, can't we? Fourth one. Yeah, that's the only thing we can say, because MA and MB, we don't know what their fraction is. Are they double or anything? We can't say like that, right? We can't say about them. So yeah, this would be the best ideal conclusion. Fine, let's move on to the 22nd question. What is this? As shown in the figure, three identical masses are connected by light inelastic strings. If these strings go over light and frictionless pulleys, okay, these strings go over light and frictionless pulleys. If the system is at equilibrium, ratio A divided B is equal to. Fine. Now this is a good question where you have to analyze it carefully. Three identical masses. So let's mark the masses as M. This is also M. This is also M. Okay. So all of them will have M, and the system is at equilibrium. That is a very important statement. So there will be, you have to mark the forces, na? Mg. This is also Mg, and this is also Mg. And there will be a tension acting here, right? So if you take this tension as T, Since the string is light and the pulley is smooth, we can say the same tension will act here as well. Hope you can agree with me on that. I'll take it as T1. Yeah, for that matter. T1, never mind. And here there will be another tension T2, and the same tension will be. I mean, let's not complicate things. I'll put it T. Now, since this object is at equilibrium, T is equal to mg. You know that this object is at equilibrium, so downward force should be equal to upward force. Simple as that. All right, fine. And here, if you take here, same tension will be acting here, so I'll mark it as T. Now, this is also T. Why is it T? Because here also T is equal to mg. No? So there's no point need to mark that as T1, T2 and complicate things. Same tension will be acting here as well. Okay. Right. So it's the same tension. And now let's analyze. Same tension here. Right. Fine. Now we are supposed to find a relationship between this A and B, the lengths. That means you definitely need to know these angles. You have to know something about these angles. Then only based on the angle, if you take the tan value for the angle, you can come up with an answer. That's the plan. Okay. Right. So I'll mark the angles as theta 1 and theta 2 here. Let's take this angle as theta 1 for the time being. Right. Theta 1 and this angle as theta 2 for the time being. Okay. Theta 1 and theta 2. Right. Good. Okay. So this is the setup. Okay. Now since this is a bit congested here, I'll draw that again down separately. Right. So there is a mass M, and what are the forces acting on that mass now? There is mg acting on it, and there are two tensions acting on, but the tensions are equal, and we have proven it why they are equal. So the angles is right. Fine. Good. Moving on. Right, so this is T, this is also T, this is mg, and the interesting part, this T is equal to mg, this T is also equal to mg. All right, and if you take these angles as theta 1 and theta 2, there's no point in that. I mean, okay, without wasting time now, three forces are acting on a body. Three forces acting on a body like this. Will not waste time. Three forces acting on a body, equal forces for that matter. Equal forces. I mean, the value is mg, 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 mg. That means this is the object can be at equilibrium only when these all three angles are equal: 120, 120, 120. Okay, 100, because three equal forces, three forces of equal magnitude acting on an object. The object is at equilibrium, so the resultant force must be zero. The resultant force can be zero only if the equal magnitude forces are at angle of 120 between each other. Therefore, this whole angle is 120. So theta 1 and theta 2 each should be 60 and 60. It should be 60 and 60. 60 and 60. All right, fine. So what are we supposed to find out now? We are supposed to find out A and B. I hope this is clear to everyone. Three equal forces acting. That means these angles, all these angles should be 120. They have not given it like that to confuse you. They have not given these two angles equal. No? They are trying to confuse you. You should not get confused. You have to be careful there. Right, fine. Now, if you consider this part, they have given us a triangle-like thing, okay, like this, and they have given this height to be B, and this whole length is A. This whole length is A. But now we have established that these two angles are equal, and they are they are 60 each. 60, 60. This is 60. This is 60. All right. This is this. Fine. If this is 60, now this side has to be half of A. This is A by 2. This is A by 2 because the angle is bisected. Therefore, these two should be equally separated. A should be equally separated. A by 2. Here B. This is B. Good. Now take this angle. Take this triangle. Sorry. Take this triangle. Very easy. What can we say in this triangle? I can write tan 60. Can't I? I can write tan 60. That is equal to opposite side divided by adjacent side. A by 2. B. A by 2 divided by B. And what is tan 60? Root 3. A by 2 can be written as A over 2B. A divided by 2B. Right? I think we are supposed to find out A divided by B. So A, that will give you 2 root 3 is equal to A divided by B. 2 2 root 3 is equal to 8. So the answer for this question is actually the fifth one. Okay. If you introduce unnecessarily T1, T2, theta 1, theta 2, I did it, but I didn't have, anyways, I just explained it to you quickly. That would make things complicated. So try to solve it one step at a time, considering all masses to be equal and tension throughout the string to be equal. You will end up in this concept. So this angle is actually 120, should be bisected by this line. So that's how we came across this answer. All right, 23rd question. 7,500 kilogram of water was pumped out of a 100-meter deep well within an hour. If the efficiency of pump is 50%, power of the pump in kilowatt. All right, fine. Now, since they talk about efficiency, let me come across this equation of what is efficiency. Efficiency is equal to desired power output. In this case, what is the desired power output? We want the motor to take out the water. We are using the motor to take out the water. So that's your desired power output, and it should be divided by total power input and multiplied by 100. That is the final equation. That's the equation for efficiency. Right? The meaning of this is you give an input of energy or power, but all that power is not used for what we intend, what it is intended to. All right, there can be power or energy wastage. Now, in this case, the efficiency is fine. I'll leave it here and let's try to find out power input is what they're asking. Power of the pump. That is what they're asking. So efficiency is 50% equal to desired power output. We don't know that yet. Total power input is the power of the pump. So I'll say power of pump. If not, I'll take that as P. Okay. You're going to take power of the pump, that is equal to P. All right. That's the value we are going to find out. That's P. Now, what is the desired power output? Desired power output, right? Now, how much energy do we need? So let's say energy consumed. Energy consumed is the change in potential energy of water. From 7,500 kilogram of water is pumped out of 100-meter well. So water is initially at 100-meter depth when we are taking up. So water is taken up by how many meters? 100 meters. So water was here, 7,500 kilogram water, and we need that water to be elevated to a height of 100 meters. That is the idea. And that must happen within 1 hour. So let's start. Energy consumed is equal to change in gravitational potential energy of water. Right. So what is the change in gravitational potential energy of water? That's the equation is going to be mgh. For m you can put 7,500. For g you can put 10, and for h you can put 100. Let's leave it as it is. Now, power consumption. Power consumption. If not desired power output, I'll write that. Desired power output. This is what we need to happen. So what is the desired power output? Now, energy we have found, that is desired energy consumption divided by time. You divide energy by time, you get power. Right, let's move on. Desired energy or consumption is this, 7,500 into 10 into 100. And how long does it take? 1 hour. When you say 1 hour, it has to be in 1 hour, 60 minutes are there. In each minute, there are 60 seconds, 3,600 seconds. Right, now we have to simplify this. How do you do that? Let's start. Zeros can be cancelled out. Okay, so this is 75, and here we have 12. Well, 75. I can say 2 here and the 25 here. Correct? If I simplify them, I'm simplifying them by 3. 3. Okay. Good. And yeah. And if you simplify this, what will you be getting? Yeah, let's leave it as it is. 25 here, 25,000 in fact, 25,000 divided by 2 into 6. I'll leave it as it is. And then I'll substitute here. That's the desired power output, isn't it? 25,000 divided by 2 into 6. Right, so the power is actually equal to into 100. I can't forget the 100 there. Yeah, fine. Then 150 can be simplified. 50, you can put 1 here. For 100, you can put 2 here. And there is 25,000 over 2 into 6 divide, and 2 is there. And this 2 also can be cancelled out like this. Right, 50, 100 divided by 2 is 50, so they cancel out. And finally, you end up in this equation. That is 25,000 divided by 6. That is the power. So that is actually 4.16. 4.1. So if I write this like this, so we need the answer in kilowatt. 25 over 6 into 10 to the power 3 watt. All right, that is a 4.16 kilowatt. Because when you divide 25 by 6, it's 4.16 into 10 to the power 3. So it's watt, right? 10 to the power 3 watt is kilowatt. So 4.16 kilowatt. But we don't have an answer. We don't have an answer. I have to check with the numbers here. I'll check with the numbers, but hope you got the idea how to approach the question. So since 4 is the closest answer for the time being, let's go to fifth answer actually. 4 is the closest answer. We don't have any other answers, but anyways, I'll check with the numbers, and if there's any change, I'll keep you informed. All right. So let's settle to 5th. Anyways, just get the idea of how to do the question. There might be some printing error here. This is how you approach this question. Okay, 24th question now. Maybe this is the most interesting question in this. Right, fine. A rope of mass M and length L is kept on a rough table as shown in the figure. The coefficient of static friction between the rope and the table is mu s. The ratio between the maximum length of the rope which can hang below the edge. That means they're talking about this length. Okay, I'll take that length as x. Below the edge of the table to the total length of the rope. Right. So I will take total length of the rope equal to capital L. Okay, so read it carefully. The ratio between the maximum length of the rope which can hang below the edge of the table to the total length of the rope. So we need to find out x over L. And these are the options you have. X over L is what we are supposed to find out. All right, good. Now, to do this question, we need to introduce a lot of a few new components. I'll start with this now. We need to know mass of rope, or this part of the rope and this part of the rope. Now, the total length of the rope is L. Let's say the rope starts here. So the length of the rope which is on the table now will be L minus X. Hope you can agree with me on that. X is the part of the rope which is hanging outside. L minus X should be the part of the rope which is on the table. Okay, right. Now, if you take a rope, let's consider an equation like this. Mass of rope, I'll use this concept. Mass of rope is equal to KL, where K is the mass per unit length, mass of 1 meter, something like that. Mass per unit length, and simple L is going to be the length of the part of the rope we are considering. Length. Okay, right. So I will say the mass of this part of the rope, we'll take it as M1, and the mass of this part of the rope, we'll take it as M2. Mass of this part of the rope, we'll take it as M2. So what is going to be the equation? Now, mass, general equation is K, simple L. We'll get rid of K, no need to worry. M1 will be Kx, mass of 1 centimeter length multiplied by length in centimeter, something like that. And what is M2 then? M2 is going to be mass of rope, mass of 1 centimeter of rope multiplied by the length of the rope which is on the table, that is N minus X. So instead of mass, now we have a relationship for mass in terms of length. Larger the length of the rope, you are separating the rope into two parts now. The rope is not separated, but one part of the rope is hanging down, the other part is on the table. So we have to compare the mass between the ropes, right? It's the same rope. Mass between the parts of the rope. It's the same rope, but different length. So larger the length of the rope, larger will be the mass. Simple as that. And that can be given by this relationship. Now, working with this diagram is very inconvenient for me. So I will change this diagram a bit like this. You can see if you can compare that diagram to this. I hope you will get the connection. Let's consider the parts of the ropes as just normal masses, because that's what we are used to do now all this time. That's what we are used to do. So let's compare it as a simple case and just try to compare it like this. Instead of M2, the part of the rope which is on the table, let's think of it as a mass on the